All right, so today we're going to wrap up our discussion about limits and continuity. Although we will see these subjects come up again in later chapters, here we'll be done with chapter 1. And then when that's done, in our next session, we can start chapter 2, where we finally get to see what derivatives are all about. Okay, so let me just quickly remind you, we'd started to introduce this discussion about continuity. And so continuity of a function simply means that it is defined for every value of x, or think of it as there are no breaks in the function. Okay, so for example, if you look in the upper left-hand corner here, you'll see that this is a smooth continuous curve. It is therefore continuous because there are no points at which there's a gap or some other interruption. In other words, there's no asymptotes, there's no holes. It's just a continuous function, and it will continue on forever up to positive infinity and down to negative infinity. The one on the far right is discontinuous because there's a hole here. That probably means that there was division by 0 in the original function at that point, although there could be other reasons for this. Now down here we have a special case where there is a discontinuity, and not only that, but the curve itself starts at a completely new point and then continues on from there. So we have what's called a jump discontinuity, meaning that we go directly from the value of y doesn't continue from its original point. Hold on 1 second. Right. To go, because of the hole, we move from here up to here. This is sometimes called a jump discontinuity. And you can see it's as if we had two separate functions here. Okay. Now, formally, though, in this case where we have simply a hole, this means that the function cannot be continuous because there is no value for f of a. In other words, the function is undefined at a, which means that f of a is undefined. And that's enough to conclude that the function is discontinuous. So in other words, if you can find a point where this is true, that means the function is discontinuous. And of course, you remember, we did run into a couple of these. We had one, for example, where, I guess it was this different section. It was something like this. Actually, this was x minus 1. Now, of course, as it turns out, we can factor this. And we're left with x plus 1. Okay, but the bottom line is, though, if we try to substitute 1 into this function, we're going to have division by 0. So therefore, the function is discontinuous. Although we saw it does have a limit, whatever f of a is here, this is our limit, but the function itself is discontinuous. Now here's the jump discontinuity. And this time the limit doesn't exist either. Not only is it discontinuous, but there's no limit. Okay, here, remember the way this works is that this one has a limit because as x approaches a from the left, the function converges to this f of a, whatever it is. And then here, as we approach from the right, the function also converges to f of a, although it never quite touches it. It never actually equals f of a. It's good enough that we're getting infinitesimally close to it as we approach from either side of a. That's enough to have a limit. Here, we don't even have that. From the left and from the right, we're converging to two different points. And so therefore, not only is this function discontinuous, but it also doesn't have a limit at x equals a. So it is a different kind of discontinuity. The one with a simple hole still has a limit. This one does not. Okay, yes, and this is how we formally define. You notice how as x approaches a from the left, and as it approaches a from the right, we're converging to two different values. Now, here's an interesting case. We have a hole, but we've also got a point which represents f of a. So this is a very oddball case because f of a is defined, but it is not equal to the limit. Okay, where the limit is right here. Let's call this a star. That's our limit. But up here, we see that f of a is actually equal to this point. So they do not equal each other. And that's another indication that we have a discontinuity. So actually, when I was drawing these pictures up here, I left that one out, it looks like. Let me add that to our collection here. That would be another way in which we can have a discontinuous function. All right, so yes, that covers them all. All right, the first one is continuous. The other three are discontinuous in three different ways. And then formally, you can prove it by showing, in this case, for example, the limit does not exist at a. Therefore, we are guaranteed that this is not continuous. Here, we're seeing that the limit does exist, but it is not equal to f of a. And here we do have a limit, but f of a is undefined. Okay, so those are the three reasons why the function is discontinuous in these three cases. All right, so just to summarize, a function is continuous at a point only if the following three conditions hold. Number one, f of x has to be defined at x equals a. The limit has to exist, and the limit has to equal f of a. Okay, so if all three of these conditions are met, we have a continuous function. Okay, now, of course, like so many other topics, we'll see this again as we go along throughout the course. But for now, it's enough to recognize these are the three things that are required for continuity, and each one of these individually can trigger a different kind of discontinuity if it's false. Okay. So here's a quick reminder of what a polynomial looks like. A quadratic function, for example, is a special case of a polynomial. A cubic function, a linear function, they're all special cases of polynomials. A rational function, as you recall, is defined as the ratio of two polynomials. For example, x squared. Polynomials are guaranteed to be continuous, okay? Because there's no value of x that can cause a hole in the function. And we're guaranteed that the limit exists everywhere and that f of a equals the limit at every point. So therefore, any polynomial, no matter what the order is going to be continuous. Rational functions are different because because you're dividing, you can have a value of x which violates one of these three conditions, and therefore you can end up with a discontinuous function like this one. It can't be continuous because you can see we have an asymptote here, a vertical asymptote at x equals 5. So the limit does not exist. Of course, you can tell just by looking at this graph, as we approach from the left, the function converges to negative infinity. Over here, as we approach from the right, the function converges to positive infinity. Okay, since they're not equal to each other, that guarantees us that the limit does not exist, and that in turn means that the function is discontinuous. Okay, so now these are the names you often see listed in calculus textbooks for the different discontinuities. They all have special names. This one, the removable discontinuity, means that if you were to fill in a value for a here, you would have a continuous function. That's why they call it removable. Now remember, this is discontinuous because here's the limit. And here's f of a, and they're not equal to each other. All right. So, but the name that we associate with this is a removable discontinuity. A discontinuity, you can see here, the limits are different approaching from the right and left. So while f of a exists, and it's right here as a matter of fact, but the limit does not. And that's the reason why it's discontinuous. Okay, and again, that's because as we approach from the left, we're getting a different limit than if we approach from the right. So the limit does not exist. Now this one, there's no limit here either. Wow, this one is really in trouble because the limit does not exist. And neither does f of a. So we really have a discontinuous function there. In other words, you can see that we actually have here as an asymptote. So this function is clearly discontinuous. All right, now here some you may run into these types of problems with the assignments. Here's the function. What kind of discontinuity are we looking at here when x equals 2? Now, I would remind you that when we have something like this, we can see right away that there's going to be division by 0 when x equals 2. But we can reduce this to x plus 2. So this is the case, we've seen this before, there'll be a simple hole there, okay? But the function is converging to the same point from both sides. So here's 4, and here's 2. And again, as x approaches from the left, the function is approaching 4. As we approach from the right, the function converges to 4 or approaches 4. So f of a does not exist, but the limit does exist. Actually, in this case, it's f of 2. I might as well just plug it in there. A is 2 in this case. And then the limit as x approaches 2 equals 4. So the fact that these are, the f of 2 does not exist, we do have a discontinuity here. This is the one that's referred to as removable discontinuity. So, that's his terminology. I mean, I guess they could have called it a discontinuity with a single hole or something. It doesn't sound very elegant. It's called removable because we could, in principle, define a point here and then take care of that problem. So removable discontinuity, it's called. Okay, meaning it just has a hole. Because the function is discontinuous, and yet the limit does exist at that point. All right. Oh my God, one of these. The dreaded piecewise function. So here's what we're going to do. Let's plug these numbers in and see what happens. Let's say we want to know the limit as x goes to 3. Well, we can see that it doesn't look very promising. So to get the limit from as x approaches 3 from the left, we substitute 3 into this function, the top, I mean. Okay, but then if we come from the right, we have 4 um, times 3 minus 8, 12 minus 8, or 4. So that's the one where we have two different values. Yeah, actually, the top one is a parabola that faces down, so you may have something like this. This is a straight line, so it should look something like this. And so this is, remember when we have two segments here, let's go back and look at the list. Um, this is what we call the jump discontinuity. Okay, jump because the function basically jumps at that point from one level to the next. So this is what we mean by jump discontinuity. So you can imagine it jumps from here to here. Okay, that's the origin of the name, I believe. It's called a jump discontinuity. And then, well, okay, we don't have a separate example here of an infinite discontinuity, but we know that it means that we have a vertical asymptote. Now, sometimes what's interesting is that we may want to know if a function is continuous, but it's possible that we can focus our attention only on a single interval. Sometimes, if we need a function to be continuous, it may be enough for it to be continuous over a single interval rather than the entire real number line. So maybe, for example, we have a function that looks like this. But for whatever purpose we are using it for, the relevant range is from, let's say, here to here. Okay, so within that range or interval, the function is continuous. So it may be that we can use it even though it's discontinuous outside that range, depending what the application is. So a function is said to be continuous from the right if the limit from the right equals f of a. Okay, so don't forget this little plus is here. So let's see an example of this. Oh, well, here it is. All right, first, let's see if it's continuous from the left, if the limit from the left equals f of a. All right, now we need some examples. So here, now I've already done this graph in Symbolab for you. And you can see that x cannot be 0 because otherwise we'll have division by 0. Oh my God, look at this disaster. I wouldn't have expected it to be quite that messy. So clearly at 0, we have an asymptote, but in fact, I'll tell you what, let's go put this back into Symbolab for a second. We seem to have two asymptotes. So we have x minus 1 divided by x squared plus 2x. Okay, I've got to get used to the way I really it's very clumsy the way it accepts ratios. Like if you don't have the mouse in exactly the right spot, it's just going to erase what you've done. All right, so yeah, here is the graph, but um, the asymptotes, the vertical asymptotes are -2 and 0. Horizontal is 0. Now the 0 horizontal is more straightforward because that implies that there's no value of x, which would cause this ratio equal to 0. But here, the -2 and the 0, let's see why. F of 0 leaves us with division by 0. Okay, what about f of -2? Okay, what happens when x equals -2? With -3 over 4 minus 4, there you go. It also leads to division by 0. Now, actually, the reason why we didn't, you might not notice this right away, is if you rewrite this, you see now it's more clear that if I let x equals 0, I'll get division by 0. If I let x equals -2, because we have x plus 2 here, that's also going to lead to division by 0. So we have the two vertical asymptotes. Okay, so that means the domain, by the way, is everything except -2 and 0. But so the function itself is clearly discontinuous, but it is continuous within each of these intervals. Okay, in other words, except for the two asymptotes, these are continuous functions. So if, let's say, we're working on some application where the only numbers that are relevant are, let's say, the positive numbers, then the fact that the function is discontinuous for the negatives is not really important. Okay, so we could come up with a solution to whatever we're trying to solve for because the function is at least continuous over the interval that we're interested in. Like, for example, the interval of possible outputs of our product. All right, now here is a discussion about composite functions. Now, I just want to quickly remind you what that means. Let's say, for example, you have two functions. The composite function f of g of x would be solved by taking within f of x, all the x's are being replaced by g of x. Okay. And so now we just substitute. And we end up with x squared minus 6. Now, g of f of x means for the function g of x, we're replacing x with f of x. Okay, so here I've got f of x squared minus 7, which means we have x plus 1 squared minus 7. And if you apply FOIL to this, f is these two, O is these two, I would be these two, and last would be these two. So that means this becomes 2x squared plus 2x plus 1. All of that is minus 7. And that's our final result. Okay, so just a quick review, quick refresher what composite functions are. So you can see we're going to need them here because we're going to talk about limits of composite functions. So basically what you're seeing here is a technique that makes it simpler to calculate these limits. So imagine we have f of x is continuous at L, and the limit of g of x as x approaches a is L. Okay, yes, we do have an example here. Oh, I skipped over the important part, the definition. So if these conditions hold, then we can calculate the limit of this composite function as f of L. All right, that's very abstract. Let's do an example here. So we have, wow, isn't that the function I just chose? Ooh, well, that was an interesting coincidence. Um, yes, so f of g of x is x squared minus 6. Fine. Okay, I probably just remembered having seen it when I was writing these notes. So x squared minus 6 is our composite function. So what they're telling us is that the limit of g of x, just g of x by itself, as x approaches 3. So remember, g of x is right here. So I'm just basically plugging in 3 for x squared. I have 3 squared minus 2, which is equal to 2. Sorry, 3 squared minus 7 is 2. So the long and the short of it is that then the limit of the composite function could be calculated simply as f of 2. Okay, that's why this can be helpful to us. So now that we know that the limit of the inner function, by the way, when you have a composite function like this g of x is the so-called inner function. And this f is called the outer function. So once we know the limit of the inner function, we can solve for the limit of the entire composite function as f of L. Okay, that capital L, by the way, is this 2. Okay, what we called L in our formal definition is that 2. So what we have here is f of 2 now. And remember, f of x is x plus 1. So therefore, f of 2 is 2 plus 1, which is 3. By the way, I do want to point out that this is not the only way to solve for this thing. If you're willing to calculate the composite function yourself, remember we determined that f of g of x is x squared minus 6. Well, if that's the case, then the limit is just 3 squared minus 6, which is 9 minus 6, which is 3. Okay, so in other words, you could have just solved for the composite function yourself and then taken the limit the normal way. But the theorem could save you some time depending on how complex these formulas are. All right, now here's an interesting result in calculus, the so-called intermediate value theorem. Now, we're not going to do any proofs in this class, although they will probably show it to you in the book. They're not going to ask you to actually do any proofs. That will wait till a much later class. Like if you're a math major, you may run into this in Calc 4 or whatever they choose to call it. Right now, you're learning the foundations, but at some point, you have to be prepared to start proving your results if you really want to be a mathematician. So what they're saying here is that if we have a function that is continuous at least over the interval from A to B. And you notice how it's a closed interval, meaning that it includes both endpoints. If the function is continuous over that interval, and Z is some real number that is between f of A and f of B, and by the way, this will make more sense when you see the graph. Then there exists a number C in AB such that f of C is Z. All right. So let's look at the graph. You're not going to be able to get the grasp of this without looking at the graph, I think. So what they're basically saying is, look at this graph. We have the two endpoints A and B. We're guaranteed that the function is continuous in this interval. Here's our f of A, and here's our f of Z, f of B rather. So what they're basically saying to us is that there is some C in between these points. It doesn't matter where, somewhere in between the two is the C, where its value is also in between A and B. Okay, so in other words, there exists a number somewhere between A and B where f of that number is in between f of A and f of B. Now, you're probably wondering, what are we going to do with this? Well, a lot of these theorems, we'll have to wait to see when they come in very handy. They will eventually. I mean, all these theorems are very useful, but it may take a while before we actually need it. But it's important to know what this theorem is all about. But this all depends on it being continuous. The function doesn't have to be continuous everywhere, but as long as it's continuous over the interval A to B, then this result holds. Now, infinite limits. We've run into this already a couple of times. Usually they involved asymptotes. So we can have infinite limits from the left, infinite from the right, two-sided infinite limits. Okay, so here's an infinite limit from the left. Okay, so basically, you can imagine what this looks like. Here's your C. And so this x equals C is an asymptote. Okay, the function is getting closer and closer to infinity without ever actually reaching it. If we're coming from the other side, oh, this is negative. Sorry, it's coming from the left, but it's negative. That would be this case. Right. Well, I didn't draw it as well as I could have, but you get the idea. As we're coming from the left, the function is getting smaller and smaller and smaller, and it is in the limit converging to negative infinity. Then we have the same ideas from the right. This could be anywhere. It'll look something like this. As you come from the right, x is getting really, y rather, is getting really, really large, and it is converging to infinity. And then we can also have this case. It's just shrinking and shrinking and shrinking forever. Okay. In fact, you've seen this before with a log. In this case, the limit of this function as x approaches 0 from the right is negative infinity. Okay, because this vertical axis is an asymptote to this function. So that would be an example of this. And of course, we can have two-sided limits where they either x is approaching, as x approaches C from either side, the function converges either to positive or negative infinity. You could have something like this. They're still trying to fix my tablet. It's not going well. I have a feeling I'm going to have to buy a new one. The one I have here is kind of a old one, and it gives me trouble very frequently. Yeah, it gets into these moods where it just wants to scribble all over the place. Um, Hold on one second. Ah, Jesus. It really annoys me to no end when it stops working correctly. Okay, this is what I wanted you to see. So you can see as x approaches zero from the left and as x approaches zero from the right, either way, the function is approaching infinity. And that would be like something like this. Okay, that would have this property. And then, you can imagine something, in this case you're seeing here means you have, and then that would be for something like this. Okay, now we have some special cases. There's always special cases. It is usually worth our while to pay close attention to them, and because they can come in very handy in certain types of problems. Um, for example, this one, well, that's interesting. This one goes to infinity. Okay. Huh. Wow. So here's an example of this one. 1 over x minus 5 to the fourth. Okay. So as we approach 5, okay, this is what we get. Okay. So we have 1 over x minus 5 to the fourth. And then the asymptote, the vertical asymptote is, of course, x equals 5. So as we approach from the left and from the right, we're going to get the function converging to infinity. Okay. And so whenever it has this form, x minus some constant or other, as we approach that constant, we're going to end up with infinity as our limit. But, okay, now, but, here's the big but. They forgot to mention this, didn't they? That's only true if n is even. Um, if n is, sorry, wait a minute. Oh, okay, now wait a minute. Yes, no. If this is even, then we're fine. But if this is odd, let's say n is 3, then you're going to get different limits coming from either side. So this would be, okay, here we go. 1 over x minus 2 to the third power. So you see here, there is no limit where x equals 3 because as we approach from the right, the function is converging to infinity. But down here, as x approaches from the left, the function is converging to negative infinity. So therefore, the limit doesn't exist. All right. So here, oh no, I didn't. You know what? I didn't even see it. It does say if n is a positive even integer. I actually overlooked that. Yes, it did say it right there. Even means you're going to get this. Positive infinity is your limit. If the exponent is odd, then you'll get this case. All right. All right. So anyway, so that actually wraps up our discussion about limits and continuity. Um, so here's what we're going to do. The next session, we'll start with the definitions of derivatives, and then fairly quickly, when we're finished with those, and you'll see, by the way, that they're tied directly to limits. Then we can learn the rules, just like we did here. Basically, we start out with some theoretical results, and then we learn the rules for actually calculating derivatives, or in this case, it was limits, and now we're going to do derivatives. So the thing about derivatives, though, is that there's a lot more cases we might encounter. So the rules, there can be a lot of rules. And in fact, the book almost certainly, I didn't double check this, but the book almost certainly has a table in there somewhere with a huge list of all the rules for derivatives, because it's quite a few. Not so much limits. There are several cases in limits, but nothing like with derivatives. Derivatives can have a lot of different situations we might run into. So it's a much more complicated idea. But at the same time, though, it's critically important to everything that follows in calculus. Ultimately, derivatives are at the heart and soul of almost everything we do in calculus. So, and in math in general, I think. So, or at least applied math. So it's going to be a very interesting topic when we get there. So here we'll wrap this up a little early tonight, and then next time we'll be looking at our introduction to derivatives, see how they're formally defined, and then start to learn how to use the rules. All right, so we'll see you all then.